Can you see this slide before just I walk you through it? Because this is essentially just a recap of what we went through last session. The multiplicative group of units mod n. Can you see the slides properly? I mean, this slide. What about the sound? Okay, you can hear me perfect, yeah? Okay, good. So, okay, without wasting time, it's pity that the cursor is not is not showing up. I don't know why, but yeah, I guess we can figure it out later. In the last session, we defined for an n, we defined Zn. You know, we know what Zn is. We define the multiplicative group Zn star, right, to be the set of all elements in the Zn that have, you know, multiplicative inverse in respect to the mod n multiplication, right? And I think we went through some examples, you know, toy examples with concrete examples, right? And another way of defining Zn star is like this, you know, the set of all A's in Zn that have GCD of A to the n to be equal 1, where GCD, this is greater common divisor of n and of A and n. Okay, so this is another way of defining the same thing, right? And another thing that we saw is that this Zn star forms a group under mod n multiplication, right? This is not, I mean, this is already like something that I believe you already figured out, and through the examples too. Here's some toy examples. So Z4, for instance. So it's actually good if you can find typos. If there is a typo, you can correct me. But the claim is that based on this, Z4 star then is like this set here, and this is a group under you know, mod 4 multiplication. The same with Z, you know, for Z5 under mod 5 multiplication, the subset of it, which is Z5 star, made of all the non-zero elements of Z5. The claim is under mod 5 multiplication. This is a group 2. And the same for mod, interestingly, the same for mod 7, right? For Z7, we have the same thing, all the non, so if we remove 0, we have all the, essentially all the elements of Z7. So the act of removing 0, it seems to, you know, generate a group automatically. This is very interesting. Those of you who are advanced, you can see there's something very interesting looking at this. For example, 5 and 7 are prime numbers, right? So this is something, it will become obvious in the next slide. But something also, if you went through examples, you know, something that you must have realized is that at least you must have some gut feeling without necessarily having to prove it, is that for most n's, for most numbers n, Zn star is generally not a cyclic group. Okay. Did anyone had a hint about this? Yes? Could you, through the examples, did you kind of had a kind of a hint, some sort of a, you know, intuition, or like some sort of a clue that actually for most n's, Zn star, the multiplicative group Zn star is generally not a cyclic group, right? And then the question is, under what circumstances do we have Zn star to be a cyclic group? Can anyone throw a clue? Just it's also a way of testing if I'm on, because anyone? Am I still on? There might be more than one circumstances, but at least one. Okay, Bren saying prime. Okay, n prime. Okay, anonymous. Okay, okay, okay. As you can see, prime numbers are everywhere. This is where, even though this is not a number theory thing, this is a group theory. Actually, one part of the session, as you will see, is the connection between number theory and group theory. Even though we'll try to avoid group number theory as much as possible. Yes. And in fact, this theorem will tell you that. Let's see, the cursor is not moving. Before actually we figured out about under what circumstances Zn star is a multiplicative group, I wanted to avoid the notion of field, but I think it helps if we actually define the notion of field, so we get it out of the way, so you know what a field is. I know most of you already know what it is. For those of you who don't, here's an opportunity. So a field is a triple, okay, made of f plus and this notation times, essentially consisting of a non-empty set f and two binary operations, plus and times, such that the following two conditions hold. So f under the binary operation plus forms an abelian group with identity that we call 0, okay? F star under the binary operation times forms a group with identity where this F star is a set of all non-zero elements of this set F, okay? So this is a group. So if you remove 0, this identity, this thing that happens to be the identity on the additive on the abelian group, then you should get a group, okay? And by convention, whenever, this is just an abstraction, right? This is just notation stuff. I could have used different notation and so on, but yeah, I'm using this additive notation, so additive and multiplicative notation, because this is much more familiar. We are all familiar with this. So whenever the two binary operations are understood, instead of just writing the triple, we just use F, okay? And this F star is called the multiplicative group of the field, okay? And when the field is finite, there's another name for it. This is what cryptographers use. It's called Galois field, okay? If it has finite number of elements, okay? Otherwise, it's an infinite field, okay? Now, here's the first challenge that I want you to go and think about. You don't need to prove it, but just to have some sort of, a feel of it. I guess with examples, you should be able to arrive to the conclusion. Is it true that the multiplicative group F star of a field is always abelian? Okay, so that's the thing, the first challenge. Okay, before I move on to the next slide, is there any questions about the definition of field? You can see how the notion of group help us have like a much more cleaner, compact, short definition of field. If we were to define field on its own, we would have all this associativity, distributed, all in the axiom. But these are all observed under the group axioms, right? Yeah, Dimitri is saying I think we need distributive layer, but well. Is that actually is there a condition? That's actually an interesting observation. There is a typo. There's something missing. Yeah, the interaction between the two binary operations, right? Between plus and yeah. Who agrees with the Dimitri? I made a typo. I forgot one extra condition. Do you agree? Which is the interaction between the two binary, how the coexistence, how the two binary operations they coexist with each other. Okay. Okay, so George agree, and it's true. Yeah. Yeah, so there's one more condition to be added here. So I kind of left it actually. I realized this thing when I was coming online, but I decided to leave it to see if you would spot it, the most advanced one of you guys. And yes, you're right. For those of you who haven't studied field theory, there is Dimitri and George are correct. You can see there are two binary operations, but the two binary operations need to interact with each other. And this comes through the notion of distributivity law between the two binary operations. I'll correct this slide and then upload this thing on the thing on GitHub. Okay. So well done. Thank you, Dimitri and George. Okay. So Amir is saying, is a field not a ring because of F? Well, yeah. Okay. So that's George. George is already taking the answer. Well, a ring doesn't need to have a multiplicative inverse. That's the thing. In a more concrete way to see this, you can see that in a field, division is always possible. Dividing between non-zero elements. That's essentially, this is what the abstraction of field is giving you. That's why fields also, there's another name in the early days, they used to call them division rings. Okay. Okay, so let's go through some examples just to build up your intuition. So we have both a case of infinite fields and finite fields. Let's consider the set of integers. This actually fits well with what Amir was saying. Amir's question. So let's consider the set of integers under the ordinary addition and multiplication. Is this a field? Who thinks it's a field? Yeah, I see there's another point that Bob is asking is whether the two binary. Yes, you would have to be, because both have the identity, right? Because, being groups. So if they are both, then, they would have to have some sort of, yeah, exactly what George was going to say, because then the identity of one would be the other. So like in the case of 0 equals 1, like George is putting on the thing on the chat, for instance. Right. Okay, so remember, for a field, you have, in respect to one binary operation, it is the entire set. It is actually a group. But then if you remove, in respect to the second binary operation, which is multiplication, if you remove the identity, the 0 identity from the additive binary operation, from the addition, then you get a group. Yeah. Okay. So this question here. So Z is clearly not a field, right? Everyone agrees? Is there anyone who has doubt that Z is not Z, the integers with addition and multiplication, is not a field? Okay. Okay, so let's look at, I know there is one axiom. So to Amir, it's not clear. So look at the axioms of field. I know there's one distributivity law, but that doesn't matter. Just look at the thing, on the multiplicative side, So if you remove 0 from the integers, do the integers have a multiplicative inverse? They don't, right? In other words, yeah. There's someone. Okay, makes sense. Yeah. Okay, so that's why the integers is not the integers is not a field. It is a ring, right? But it's not it's not a field. It is a ring. It is in fact also a group under addition, right? So under one of the binary operation, it is a group, but it fails to be a group under the second binary operation when you remove the thing. It fails to be a group. Okay. What about the rationals? Yes, it is a field. Yeah. What about reals? I guess this is also trivial. Yes, these are fields. The set of complex numbers, yes, because the field of complex numbers, as we say, in algebraic lingo, it says, it's an extension of the reals. So yes, we're talking about field extension. Yes. Now this is the trickier one a little bit. For those of you who are a little bit advanced, who've seen this already, I think you already know the question. So Z2, is this a field or not? In the next slide, you will know why. It is a field. What about Z3? The claim is also, it is a field. What about Z4? Is Z4 a field? No, it's not a field. What about Z7? Sorry, Z6, not Z7. I'm already jumping. This is also not a field. Does anyone have any doubt why Z4 and Z6 are not fields? They are rings, yes, but they are not fields. More or less the same argument as we had with the Z, with the integers. Yeah. Also, they don't have the thing, but Barry actually hinted at something more fundamental than that. The thing, yeah, because they're not primes. Yeah. And this brings me to the next to this thing. This could have been I could have framed this as a theorem, but I just put it like an observation, a note. So if P, maybe I should have used N. It doesn't matter, just for you to get used to it because of the notation here that I will tell you in a minute. So if P is a prime, then ZP is always a field under mod P addition and multiplication. Okay, and we can also generalize this to say that in general, Zn, is a field in respect to mod N if and only if N is prime. Okay. In particular, the multiplicative group when ZP, this is why now you start to see why the Z5 and Z7 had the coincidentally, incidentally, when we removed 0, it's still like all the elements. So you have this when P is a prime, then ZP star has this form. Okay. Now, there's another thing you need to be aware. So first of all, this Zn star, we are using a bit of abuse of notation here. Normally in the thing, people use the quotient notation, which I mentioned in the previous session. But for us, it doesn't matter because we understand exactly why what Zn is standing for, right? If you are like a number theorist, this might be confusing because you might think we are dealing with the p-adic numbers and all this stuff, but it's not. Yeah, okay. And another thing is that when P is a prime, a notation instead of ZP, people normally use FP. Okay, so this is the notation, and so the multiplicative group of the field is then written FP star. Okay. As I already said, these like finite fields are known as Galois fields, and also an alternative notation to this is where you have to, it's just notation stuff. It's just one of those things that you have to get used to. Cryptographers very often write GF of P, or sometimes you see GF of P, or power of a prime number, or something like that. Okay, so it means this. Okay, it means the Galois. This thing. We will use FP whenever instead of ZP whenever P is prime. So we fix our notation. Okay. So the question is the multiplicative group, so given a finite field, let's call it prime field because of the P, okay? Is the multiplicative group F P star cyclic group? Who thinks yes? Who thinks no? Okay, so Dimitri thinks yes. Anyone else wants to throw the hat? What's the gut feeling? Is this a cyclic group? FP star. I mean, if you have gone through if you had time to go through the exercises, some of the toy examples, maybe you would have a hint, but that doesn't matter. Anyone else? Before you find out the answer? Okay, so Amir thinks yes. Excellent. Anyone else before we jump? Confidence, yes. Okay, so George is not sure. That's very interesting. Anonymous say yes. Okay. Anyone else? I like this actually, especially when there is like someone or the other. You know, who else thinks it's not? So at the moment, there's only one person who thinks it's not cyclic F. So FP star, where P is prime number, is not cyclic. There's only one person, so everyone else thinks it's a cyclic group. If it's a cyclic group, then it means that it must have at least a generator, right? So there must be an element in this multiplicative group that generates the entire group. Another go? Yes. Does anyone? George, have you changed your mind? Okay, yeah. So I claim you will be able to see now with this thing called the primitive root theorem. This is this was phrased in a little bit more friendly to group theoretic lingo. So if you pick a number theory book, this might be phrased differently. Okay, so we try to. I'm using something a little bit more in the context of group theoretic lingo, so it's more familiar to you, right? Because we are talking. This is a group theory crash course. So the primitive root theorem says if FP is a prime field with FP star, the multiplicative group of FP, then there exists at least an element in the multiplicative group, a generator in the multiplicative group. Okay, so this essentially means that the multiplicative group FP star is always cyclic for any finite field FP. Okay, so if you are a number theorist, you don't say generator, you say primitive root. Obviously, we are here on the group theoretical lingo, so we will call them generators. Okay, but generators and primitive roots is the same lingo. It's just number theorists use one lingo. The group theory, obviously, this actually puts. This is very actually very interesting in one way, because you see how two branches of mathematics, are intertwined together, even though the lingo is slightly different. But this is actually very, very, very interesting also, because it tells us, because this multiplicative group, we know how to build them, right? We know how to do computation on them, right? So if we wanted to do something with with cyclic groups, these guys are the first stop for us, right? Because it's easy. We know how to do additions, on this, how to do binary stuff on them, right? So This is very, very important. So this tells you that now you start to see why cryptographers love this the finite fields, this FP, right? So here's an example, right? So remember this in the previous slide, I was using Z notation. Now I'm using F, right? Just notice this because obviously this is, we decided to fix because this is a field, FP is a field. So instead of using Z notation, we are using F5 star instead of Z5 star, okay? But it's essentially the same set, as you can see, right? So the question is, now given these examples, you can see these generators. You can also correct me if there is a typo here. Okay, that's a very good question. Yeah, Dimitri is saying, isn't every element except one a generator? That's a very good question because this actually leads to a natural question. Given a prime number P, how many generators are there for the multiplicative group Fp star? Or if you wanted to be a number theorist, how many primitive roots are there on the field Fp? So that's how you would phrase it, the same question. Okay, any guess? So Dimitri is saying except one. Based on your extrapolation, then let's assume you are right, Dimitri, except one. So then how many? So in the case of F5 star, okay, so he found a counterexample, okay? Okay, that's fine. Okay, that's good. Okay, so you will have the answer now through this. This is a theorem. So it says let's Fp be a prime field and the Fp star be a multiplicative group of Ft. Then there are exactly phi of P minus 1 number of generators in the multiplicative group Fp star. Well, remember this phi is the Euler's twisting function. We covered it last time. So if you know how to compute it, you know exactly how many generators this multiplicative group has. This is great, isn't it? Now, to keep you practicing, so I'll give these examples. These maybe two of them are more or less toy. The other ones start to be a little bit complicated. So the question is, consider these multiplicative groups. So F11 star, F29 star, F43 star, F79 star, F97 star. These are all prime numbers, I claim. Huh? So I hope I didn't make any typo. So the question is, how many generators are there for each multiplicative group? Okay, well, you already know that, the formula for you know how to get there. In the previous session, you know how to compute this. So you know how to compute this using the thing, Euler's twisting function. You should be able to figure it out, how many generators. Okay, so far so good. Another thing I want to add here, now that we are, because F in cryptography, when you use the field Fp, or in our case, we are interested in groups. When you use Fp star, you generally don't just want you think you just want a very large prime number and this type of stuff. Actually, you also want something else. You want the prime number to be safe. The reason for this, you will figure it out once we touch the cryptographic side of it. We'll skim through it, but you will understand once we talk about the Diffie-Hellman key exchange protocol, because there is an algorithm that can solve the underpinning problem. If the P is not a safe prime, it can be subjected to that attack. But that doesn't matter at the moment, okay? So let's see if I get this definition correct. So a prime number P is said to be safe if it can be written as on this form, okay? So there exists another prime number, let's call it P prime, such that you have this, okay? And this P prime is called the Sophie-Germain prime of P. Okay, here are some quick examples. I hope I didn't make a typo. I'm terrible with concrete examples. I guess you probably figured it out. So yeah, so go play around with this, because it will come very handy later on in the next session. And also, if you are doing any implementation, cryptographic implementation, you need to be careful which type of prime numbers you pick. Huh? Now let's go to the notion of discrete logarithm over cyclic groups. Before that, the notion of discrete logarithm can be defined on an abstract group, okay? But for the sake of the thing, we will, for our purposes, because we are interested in the Diffie-Hellman key exchange protocol, and we are interested in the FP star, this this multiplicative group, which is cyclic. So we will focus on defining, instead of going too abstract, we will focus in narrow our definition of the discrete logarithm to just cyclic groups. Okay, so here's a definition. This is more like a definition type theorem, okay, because it's a fact. Do you agree that given a group, a cyclic group with a generator G of order n, okay, then for any x in G, there exists a unique integer k, between 0 and n minus 1, such that G to the k equals x. This is a fact of, by definition of, this is a consequence of being a cyclic group of, or G being a generator for the group. Do you agree? Do you remember the properties of a cyclic, of a generator from the last few sessions? Have I made a mistake? Who agrees? Who disagrees? Agree? Okay, agree. Does anyone has any doubt? This is just a consequence of G being cyclic and little g being the generator of the group. Okay. If you have a bit of doubts, just go back again to the previous session, where we went through this. Okay. Now, the integer k is called discrete logarithm of x in respect to the generator G. Okay. Or another, often also we say the integer k is the discrete logarithm of x in respect to the base G. So G can, if you are a group theorist, you will just say, generator. You don't. If you are a computer scientist, you normally use the word base. Okay, so it means the same thing. Okay, and then the notation-wise, we write this log Gx, which is equals to k. Okay, to denote the fact that k is the discrete logarithm of x in respect to base G. Okay, so I'm using already the name base. Okay. So here are some toy examples. You can actually correct me if I made any mistake here. Okay. So for example, in F5, 2 is a generator, right? Do you agree? Anyone disagree? Then the claim is that the logarithm of the discrete logarithm of 1 in respect to base 2 equals 4. Because obviously 2 to the power of 4 equals 1. Okay, I mean, you can just get the table, the multiplication table of this quickly and look at this. Okay, and the same here is saying, the discrete logarithm of 2 in respect to base 2 equals 1, because 2 to the 1 equals 2. Correct? Does anyone disagree? Have I made any typo? This is an opportunity actually to correct any typos. Has anyone any doubts in this in terms of the definition? What the logarithm in the group theoretic. In this case, we are defining it over a cyclic group, which makes it easier, because actually, if we had defined this in an abstract group, there is no guarantee that this thing exists. It might not exist. Okay. Okay, so just go through these toy examples and see. I did this, obviously, these examples very quick. I don't think I have any typo there, but it will be actually a good exercise if you can double check. But this is just an example, you know. So to recap, the discrete logarithm. So first of all, you need to fix a group. This is one of the things that the Diffie-Hellman protocol, the way it works. Two parties, let's say our friend Amir and Bob, instead of Alice and Bob, they agree on a cyclic group. In particular, they agree on the generator. So this is something that you have to fix. And then the question of computing the discrete logarithm then becomes just a matter of following this, trying to figure it out, finding which integer satisfy this. Okay. So this is the discrete logarithm definition, and I guess I already said, in fact, before we go to the actual description of the problem, looking at this, what could the discrete logarithm problem be, at least over cyclic groups? Can someone type on the thing? What would be the problem of finding what? How would you phrase it? Am I even on? This is where it's very handy to have our friend George. There's only one slide to go. As I promised, we will finish on the time. Okay, so Barry doesn't understand the question. I'll repeat. Okay, so yeah. For a cyclic, find the discrete logarithm. Yeah. Does anyone think so? Barry, what I was saying is that based on this definition of discrete logarithm, how would you phrase the discrete logarithm problem? What do you see the problem is? How would you phrase it? So Amir has thrown up something. He's saying for a cyclic group of order n, find the discrete logarithm k for a given x. Okay. Is this complete, or there's something else missing? Is there something else missing? A piece of information missing from Amir? Okay, that's very interesting. So Amir is now questioning whether the difficulty is in knowing the generator. Who thinks that's the thing? Well, the generator has to be is given to you. So the generator is something that is a piece of information that you need you need to have. This is what you and Bob need to agree. The generator. Based on this, how would you rephrase your thing, your discrete logarithm problem? Before I go to the slides, that actually, anyone else wants to put throw in the thing? Okay. Okay, so let's see if I phrase it correctly or properly without confusing. So the discrete logarithm problem, I phrase it like this. Given a cyclic group G generated obviously by little g of order n and an element x, compute the logarithm of x in base g. In other words, just like I think Bob is already hinting, is, in other words, just find, so the computational problem is to find this, you find the k. So we give you the cyclic group, say here's a cyclic group, here's a generator, it's of, this is a cyclic group of order here's an element, go find the discrete logarithm of it, So another thing is for additive cyclic groups, now we are going to concreteness here. This actually is no more than just solving this equation here, okay? And for the multiplicative group FP star, this is just, equivalent to solving this problem here. Okay. Now, looking at this, at these two examples, suppose you are a cryptographer and you want to build a cryptographic protocol whose security depends on the hardness of the discrete logarithm over cyclic groups, not over an abstract group. So the question is, in this scenario, if you are given the option to choose the additive cyclic group Zn or the multiplicative cyclic group Fp star, which one would you choose? I mean, look at this, which one? Okay. So, yeah. So everyone is choosing multiplicative because it's hardest, right? And this is actually saying something else very interesting here that we will probably discuss in the next session, is that the computational challenge of this actually is to do more, is more to do with how the group is represented than the actual group theoretic property, right? Because any group, cyclic group of order, of finite cyclic group of order whatever finite is isomorphic to some Zn, right? Right? But that's not the thing. Somehow, this solving this on a thing on this particular group, this problem translated in this particular group is harder than translating it than solving it in this other group. Okay. We will talk about complexity in the complexity of this in the next session. But just to show how actually, the choice of the group really matters. This is what this is telling you. The choice of the group really matters. Even though you have all this, from a mathematical, from a structural point of view, you have the isomorphism theorems and all this stuff. Actually, the choice on which group you want to formulate the computational challenge is what matters. In Zn is very trivial, not trivial. There are algorithms that can do this in polynomial time, but with Fp, this is not so. Especially when you choose P to be careful. This is something that we will do in a thing. We will come back to this in the next session. So this is what the discrete logarithm problem is. Giving a cyclic group of order n, the question is, when we give you an element of the group, and the generator, obviously, to compute the discrete log in the base of the generator. That's it. It turns out this is a very, very interesting problem that actually guarantees the security. This is what guarantees the security of the Diffie-Hellman key exchange protocol. We will see how it works, how exactly this works, how Amir and Bob can communicate, can agree on a key by sharing, stuff like a group and sharing some critical piece of information. But the hardness of this makes it harder for Eve. When Eve intercepts whatever Bob and Amir, the crucial piece of information that Amir and Bob need to share over an insecure channel, Eve cannot, because doing that would require Eve to know how to solve this, in an efficient manner. Okay, so we will leave it here because I know you went through a lot. Let's just go through it. In particular, do some of the exercises that I'm giving you, the challenges with different groups. This will give you a hint about the complexity of this. In particular about doing the things, finding this in an additive group versus finding it in a multiplicative group. So you will see the point that the choice of group is really what matters. Okay, or it's the important thing. So let's see. Challenge 3. I might not have labeled this properly. but I will double check the slides again, and I will obviously add the extra axioms for fields, which is the distributivity law that I forgot to add. So I encourage you to, it's pity the cursor is not working. I was trying to go through. I just realized that you cannot see this. Yeah. So the challenge 3 is obviously, consider the additive cyclic groups, and then you are, encouraged to identify at least 2 generators and play with those 2 generators, right? And then for each of the identified generators, you compute a discrete logarithm of at least 6 elements. Pick them, randomly, whichever you decide to pick. Yeah, just practice computing discrete log, because this will give you an intuition about the hardness for both additive but also multiplicative case. Okay, so that's it. Based on this, I will just sort of saying, because this is very important. So I assume everybody, do you understand the discrete logarithm problem in terms of cyclic groups? What the problem is? At least the way it is stated, what the problem is asking you to compute. You might not necessarily have a clue about the hardness, the complexity of it. Forget that. But at least the statement of it, what the problem is trying to ask you to compute. No one has any doubt. Yeah. Am I still on? Maybe this is the right time to try to bring George. Maybe, George, I missed something. I'll try to invite you again. So we can, maybe 5 minutes, we can wrap up, because this is the last slide, really.
Hello?
Yeah, George, yeah, I can hear you.
Okay, I can hear you this time too.
Okay, that's a good news. So
yeah, there's a lot of questions in the chat.
In the chat?
Yeah.
In Discord or this?
No, the Crowdcast chat.
Okay. Okay, so Dimitri saying it still doesn't look very hard to me. You need that the most. Okay, that's interesting. Maybe try to go through these especially challenge 4 in the multiplicative groups. Maybe increase the size of its prime number, for instance, and pick not too complicated, not too a trivial generator, for instance, and then try.
I think it gets hard when when your table gets huge of all elements. Yeah. So you can't just do a lookup.
Yeah. But the statement of the problem, is it understood? Is there does anyone have any doubts about what the problem is trying to do, or at least stated the way it is stated? Let me go back. So you are given a cyclic group with a generator. This is something that you have to be given. Okay, so it's clear to everybody. Yeah. So this is a discrete logarithm problem from a group theoretic lingo thing. This is what, and in terms of applications, this is this problem. This is what guarantees the security of the Diffie-Hellman key exchange protocol. Really, the hardness of this. In the next session, we'll see if we can mention a bit the complexity of it and these type of things. Yeah, that's also another good question we will explore. How high does P have to be in order for this problem to be hard enough? That's a very good question. This leads us to complexity stuff that we will try to touch just to give you. But in the meantime, I guess you can have some sort of a build-up intuition for yourself. Just maybe pick a random large enough prime number. If it's already giving you hassle, you can. What's your feeling, George, about this? Obviously, this is I will make a comment not today on the thing on quantum computers, about this problem, solving it using quantum algorithms. But it's
yeah, I'm not sure with quantum, but classically it seems to be rapidly growing within the complexity.
With which one? The thing with the multiplicative case?
Yeah.
Well, this is the thing. Maybe I'm not sure if I was clear what I was trying to say. From a structural point of view, every cyclic group of order, whether finite order is isomorphic to some z, some zn, right? We've seen that. Yeah, but that's not it, the thing, So this here, what it's telling you is that the choice, the way, the structure, the property of group is actually not the cyclic. The group theoretic property is actually not that thing. Is the representation, the way you represent the group is what I'm using here. Represent is in the colloquial sense as opposed to a representation theory.
Yeah, I'm just thinking that in a sense that if you take the residues mod of prime, they look increasingly random the larger the prime gets.
Yes, hold your thought on that, because that's randomness is one of the things that conditions that we will require to in order to make this a little bit as secure, tight in terms of attacks. The other one obviously being the prime number itself of FP to be safe, for instance. Yeah, hold this thought for the next session when we will go through the cryptography side of things. Obviously, we won't dive, but just to give people overview of these things.
So yes, okay.
So, has anyone come across this problem before, the discrete logarithm problem, but from another point of view, as opposed to group theoretic point of view? Was this way? I know we've been through a lot of stuff to come in. Is it much more cleaner now from this point of view than before, whatever way you were exposed to it? Anyone wants to comment? You never heard of the discrete logarithm problem, or have you seen it before, but described in a different way that's a little bit less group theoretic and maybe a little bit more complicated? I found the group theoretic version once you know what a cyclic group is, and this thing much more cleaner, in my point of view.
Yeah, I don't think it makes the problem itself any easier. It's just a different language.
Yeah. In terms of understanding what it's asking you.
In terms of understanding the problem, maybe it's helpful, but in terms of solving the problem, I don't think it helps.
Yeah. Yeah, that's exactly the point you were saying. We were saying about this not being a group theoretic thing, really. Even though from the understanding, from the expose point of view of exposing it, I think it's much more cleaner. Even looking at this, the way computer scientists expose this is even more confusing. I think the mathematician way is maybe I'm biased.
Yeah. I think I agree with that sometimes the computer science obscures things a bit.
Yeah, so, maybe some of you on the audience, you might come up with an algorithm and these things now that you understood this thing on the problem, maybe we might come up with an algorithm better than the existing ones.
Yeah, that's I think one of the oddities is that it's not provably impossible, and it's but nobody's found a good algorithm.
Yeah. So, okay. Any other comment, George? You want to any advice or some things you want feedback or something on the others?
My main advice would be to play with modular arithmetic for small numbers.
Yeah. Because it can actually, I agree, I completely agree. It can help you build that intuition in a way to give you a rough idea, right?
Yeah.
On how this thing might be, as you increase, the size of the group, right? As the group becomes, massive. Okay, so this is it. Really, this is the end of the how do you say, the beginning of the end of the coverage of cyclic groups. Now, in the next session, we will cover symmetric cryptography, then just at a superficial level, and then we will ask a question: how does I won't use Alice and Bob. I will use Amir and Bob. To use our community members' name, Amir and Bob. So how do they agree? Because it's symmetric cryptography, they need to somehow they need to get they need to have the same key in order to to encrypt their messages, right? Encrypt and decrypt. So this is where we will see next how very simple property of the stuff that you went through about exponentiation, and in particular the property of a cyclic group enables you to do that. Very genuine, but very, very, very interesting nevertheless. This interesting though, before from a historical point of view, I believe the guy who came up with this protocol actually he was working for the British intelligence, for the GCHQ, but he couldn't publish. 20 years later, so we could have had this protocol out 20 years earlier if it wasn't the thing with the GCHQ. So before Diffie and Hellman came to for this, they the other guy, I forgot his name. I think. I don't remember his name even. Nobody remembers it. This is the thing. Everyone remembers Diffie and Hellman.
But it's also a message to these secretive groups that you can't keep that secret forever. Somebody else may come up with it.
Yeah, absolutely. And now actually it's very interesting because obviously these intelligence services are interested in protecting, critical infrastructure, both at economic level, but also, it means that they are somehow also they are trying to protect, companies, private companies, intellectual property, and all this type of stuff. So a lot of innovation they come in from like, protecting, the stuff they need. It's helpful if they give that to companies. They talk to industry in the respective countries. So it's one of those things. Back a couple of years ago, obviously there was this thing of more of like trying to find a back door to go and get into private companies in order to get some information about some individual or some groups or something of interest to the government or something. Yeah. Now I think they are more incentivized to collaborate with the industry and even create standards, in order to make it.
I think that they realize that a secret back door might not remain a secret, so that can come and bite them.
Yeah, exactly. So, okay. Does anyone wants to make any comment? I can bring you to stage, or we end it here. And
Okay, I guess if we are taking the time off, I can have a study session next week, unless people would rather we catch up and have another lecture.
Yeah, I mean, I apologies for the next. I realized what happened was because George, you registered late. I didn't have the opportunity to add you as a host. So I thought I forgot to. I needed to do that. That's the reason why you couldn't start the session.
Yeah.
So it was relying basically on me because I created the event to start the session. That's why you couldn't do the study session. So apologies for that. I have now taken put a note anytime steps to take in order to not for this to not happen again.
But yeah, it was really a question for the group whether they would care for another study session or rather feel like we should just plunge ahead.
Yeah. Does anyone, the ones present right now, do you want to do a study session with George to go through this stuff?
Yeah, for myself, I definitely need to review this because there are still some things that are not clear to me.
Okay.
But I can do that. Yeah, I can do that on my own time if the vote is that we go ahead and have another lecture next week.
Yeah, on that, do you want to have a double session or you want to have like the usual 2 weeks break? Because obviously we missed the thing, so we are like one thing behind. Do you want? Because the next session will be just essentially just covering the cryptographic side of things, and then we wrap up cyclic groups. But do you still have? I definitely recommend you to go through the exercises and just so you get familiar with computing discrete logarithm to see to give you some clue about how hard it is to do it both in the additive and additive versus the multiplicative group. So Bob is saying study session, yeah.
Yeah, Bob votes for the study session. So
okay, who else votes for the study session? Okay, so only Bob. So what's your feeling then, George?
Yeah. For myself, I would like to, even just for myself, to have a study session. There's a few things I think I need to review, especially with respect to modular arithmetic, but also some subtleties about the center of a group.
Okay. So you would prefer like, okay. Okay, so Beren is saying he needs a study session. That's fine. Actually, I encourage study sessions because you can go through and this is the best way of doing peer-to-peer learning.
Yeah.
Instead of over chat like on Discord. And you can share screen. Yeah.
I also encourage people in other time zones to maybe find a time when they can get together.
Oh yeah, so it's not just obviously George is available in the Eastern, which also covers some European time, but everyone else in the other time zones, please feel free to organize with someone else. The person doesn't necessarily need to be part of the community. You can organize with someone else interested in these topics. So just go through. It's important.
Yeah.
Yeah.
So to answer Berend, I wouldn't mind taking some time in the next study session to quickly review semigroups and monoids.
Okay, so thank you for that. Okay, so Berend, I would recommend you join the Discord. I don't know if you already joined the Discord, so you can coordinate with George. You can send him direct message, or send it on the thing, so you can exchange, organize yourself what time and all these type of things. And once I create so is it the same time, George, the study session?
Yes, that works. The time works very well for me.
Okay. Okay, so in that case, let's do next Friday instead of a lecture. We do we continue with the thing as usual with the study session. This might also give Berend, this might also give Berend time to catch up.
And I'll be sure to register in advance this time.
Yeah. So Dimitri saying it's okay. Yeah, Dimitri, thank you for coming, and feel free to leave. And I look forward to seeing you in the next session. And yes, play with the discrete logs. It's important to see. Thank you, Berend. Yeah. So see you next time. Okay, George. So maybe we can wrap up if you don't have any other comment that you want to make to everyone else.
That was it. I think this was just a little building on what we've covered before. So it was a good session.
Okay, thank you. Well, in that case, thank you so much again for taking your time. And I see you, everyone. So thank you again, and we are getting there.
Okay, so bye everybody. Let me.
Bye everyone. I'll see now. How do I disconnect this?